Okay, I'm on page 8 of the notes packet. So previously we had learned how to sketch a solution curve to a differential equation using a slope field. In this section we're going to do the same thing, but now we're going to take a look at it numerically by computing points on the solution curve using a method called Euler's. So let's first start reviewing what we learned previously. So here's a differential equation. This is the initial value I'm giving you. Let's practice solving the differential equation again. And remember we talked about, okay, in order to integrate really the x, you need that dx on the same side. And the antiderivative dy is y. This is x squared over 2 plus c. This would be called your general solution. I do give you an initial value, which is a particular point on the graph. And if you plug that in, you're going to get that c is equal to 1. So my particular solution to this differential equation is this. So this is your analytical method, your algebraic. Okay? And then the other day we also did it graphically, which is creating a slope field. So the idea is, okay, let's say we don't know what the solution to this differential equation is. I can still create a graph that represents the slope of that solution. So it says that dy dx is always whatever the x value is. So when x is equal to 0, dy dx is 0. So I'm going to draw a little horizontal tangent line everywhere. When x is equal to 1, dy dx is 1. So I'm going to draw a little tangent line segment that gives me a slope of 1 approximately. When x is 2, dy dx is 2. So it's all going to be relative, so you just want to make it a little bit steeper than you did at x equals 1. And I'm going to do the same thing on the other side. At x equals negative 1, I'm going to draw a little line segment that has a slope of negative 1. At x equals negative 2, slope is dy dx is negative 2, and so you get the idea. So this is a slope field for this differential equation. Now the last thing we're going to do is do the same thing, but we're going to do it numerically, and it's called Euler's method. And basically with Euler's method, what you do is you come up with approximate points on the curve. So these are not the actual points on the function, but we're going to do approximations. The way I typically do it is I create it in a table format. So you will need one column for your point, another column for your dy dx, in this case is x, which is really your slope, and then you will need another column for your change in y, which is really your dy, which is really dy dx times dx. Another way to think about this column is thinking back to algebra, right? Change in y over change in x is slope. If I multiply that change in x over, delta y is m slope times delta x. So delta y is slope times delta x. So this is our language from algebra, but using calculus notation, your delta y is really dy, which is the change in y. Instead of m, I'm going to use dy dx, and then delta x is dx, and notice what happens. Okay, so this is what's happening when you do Euler's method. I'm going to show you graphically as well, but you don't need to draw the graph when you do these Euler's method problems. You should always be given a point to start with. This goes back to this original problem. I'm telling you that you know that 0, 1 is a point on the graph. So that is given, that is a point on the graph. That is the only point you're given. All the other points on the graph you're going to approximate. What I'm going to do is I'm going to come up with the slope at that point. This problem tells us that the slope is always whatever x is. X at this point is 0. So my slope at this point is 0. So at that point, it is telling me there is a slope of 0. And then what I'm going to do is use this information to figure out what the next point is going to be. So dy, but in order to get to the next point, I need to know how many units I should go up in my y value. So dy is going to be slope times dx. dx is your change in the x value. They will always give this to you. They tell you delta x is 1. So 0 times 1 is 0. Once you have this, you can calculate where the next approximate y value is. I'm telling you that delta x is 1, so x starts at 0, so your next x value should be 1. You're going up by 1. Your previous y-coordinate was 1. dy we just calculated is 0, so you're going to move up the y-coordinate by 0, so the y value stays 1. So you've just calculated another point on this graph. The next point on this graph is 1, 1. Again, this is an approximate y value to this function. We're using this idea of Euler's method to come up with an approximate value. We're going to repeat the process, and I want to get to f of 3. So dy dx at 1, 1 is 1. dy is dy dx times delta x, so 1 times 1 is 1. I'm moving up the x-coordinate by 1, so this gives me 2. Your y value was 1, but we're going to move up the y value by 1, so now we go to 2, 2. So there's my next point on the graph. Okay, I'm going to do this process again. So dy dx at 2, 2 is 2. dy is dy dx times delta x, which is 2. So your next order pair goes to 3. But then since your dy is 2, the y coordinate goes all the way to 4. So your last point would be 3, 4. So this is the approximate y coordinate on this function using the idea of Euler's method. Now in part A, we actually came up with the actual equation. If you actually plugged in 3, 4x, the actual y value on the graph is 4.5. Euler's method is a way to approximate the y value using these intervals. Euler's method will give you a better approximation if you use smaller delta x's, so you get closer approximations here and here.